Hi all. Today we'll be discussing the LeetCode problem of the day. Construct the minimum bitwise array 2. So here you are given an array nums consisting of only prime numbers. So suppose you have 2, 3, 5 and 7. So now you have to construct another answer array where answer of I will be a number such that suppose answer of I is x, then x or x plus 1 should be equal to this nums of I. So basically answer of I and answer of I bitwise or answer of I plus 1 should be equal to nums of I. And also the multiple values of answer of I will satisfy this case. So you have to minimize the value of the answer of I. So in this example, we can see that for the 7, we can fill the value with 6. So 6 in binary is 110. And 6 plus 1 in binary is 111. And if you take the bitwise OR, you will get the value as 7, which is equal to the nums of I. But we have to minimize the value of answer of I. So instead of 6, if we use maybe 3. So 3 in binary is 11. And 3 plus 1, 4. So 4 in binary is 100. And if we take the bitwise OR, you will get the same value, which is 7. And 3 is the smallest value that will satisfy this condition. So for this 7, your output will be 3. And for 5, you will have 4. For 3, you will fill 1. And for 2, you can't pick any number such that that number bitwise or the number plus 1 will give you 2. So that's why you will just return a -1. Because for this number, it's not possible. So if it's not possible to find a value for answer of A, you'll just set the value as -1. So now let's just look at the examples. So first it is 2. So 2 in binary is 10. So no matter what number you pick, the number plus 1, when you do bitwise OR with the number and the number plus 1, it won't form the 2. So for that, you put a -1. Next, for the number 3, 3 in binary is 11. So for the 3, you are choosing the answer as 1. So 1, you do bitwise OR with 1 plus 1. So 1 and 2, you do a bitwise OR. So you get the value 3. So 3 is satisfied. So next, you have 5. So 5 in binary is 101. So for this 5, you will choose the number as 4. 4 in binary is 100. So 4 bitwise OR 4 plus 1. So 4 and 5, if you do take the OR, you will get 101, which is exactly equal to the 5. So answer for the 5 will be 4. And 7, like we discussed, the answer will be 3, because 3 and 4, if you take the bitwise OR, so this is 3 and this is 3 plus 1, 4. And when you take the bitwise OR, you get the value as 7. So this field, you will have the value as 3. Now let's look at the second example. So first you have 11. So 11 in binary is 1011. So for this, he's claiming that the answer is 9. So 9 in binary is 1001. And if you do 9 plus 1, which is 10, its binary is 1010. And when you take the bitwise OR, you get 1011. So which is same as the 13. So answer for 11 will be 9. And next, if you want to look for 13, so 13 in binary is 1101. So for 13, he says the answer is 12. So this is 12 in binary, and 12 plus 1 is 13. And when you take the bitwise OR, you'll get 13 again. So for 13, answer is 12. And lastly, for 31, 16, 8, 4, 2, 1. So this is the binary representation of 31. So for this, the answer is 15. So 15 in binary is 1111. And 15 plus 1, 16. In binary is 10000. And when you take the bitwise OR, you will get the number 31. So answer for 31 is 15. Now coming to the constraints, the array length will be from 1 to 100, and each number can be from the range 2 to 10 power 9, and it is guaranteed that nums of I is always a prime number. Now let's go over the approach. So suppose we have this number 807, and in binary it's 1100 10011. So this is the number we have to form, and for that we need to pick a number x, and you have to do a bitwise OR with x plus 1, and that should result in this number. So one thing it is sure that we know for the bitwise OR, if we take OR of 0 and 1, you'll get a 1. For 1 and 0 also you get a 1. For 1 1 also you get a 1. Only for 0 and 0 the bitwise OR will result in 0. So here we can see that we have some zeros. So if we have a 0 in our the number we pick, it should also have this bit as 0, because if it has a 1, and when you take a bitwise OR, this field will not be matching. So one thing is clear, that wherever we have a 0, there in our in our answer you must have a 0. Okay, so the 0 case is done. Now let's look at the 1. So in the binary addition, suppose we have 1010. In this, if you are adding a 1, so to a 0, if you add a 1, only this position changes. So 0 plus 1, this will become 1, and the rest will remain same, which is 101. And what if instead of 0, if you add 1 to a 1, that means if you have something like this, 1001, and to this you are adding a 1. So here what happens is, when you add 1 plus 1, you get 0, and a carry gets carry forward here. So 1 gets carry forward to the next position. So here also you add 1 plus 1, you get the value 0, and this carry is 1 is getting carry forward to the next position. So finally here you have 1 and 0, so the carry ends. So here 1 plus 0 will give you 1, and the rest of the values will remain same. So yeah, this is something we have to keep in mind. So when you add a 1 to a 1, the 1 keeps getting carry forward until you find a 0. So in our input, it is guaranteed that number of I is a prime. So all prime numbers are odd except 2. So for 2, we can have a special case that if my input is 2, I'll just put a -1. So apart from 2, any number we have, it must be an odd number. So for odd number, the last digit will always be a 1. So that means to form the bitwise OR, you can have the ones as the same, because if you put the number as 0 here, and when you add a 1 to this number, these zeros will not change to 1. So zeros will only change to 1 when the carry gets carry forward. But here, since you have a 0, so even though 1 gets carry forward, it will stop when you find the first 0. So what I mean to say is, so if you have two ones here, and if you add a +1 to this one will become 0, and 1 gets carried forward here, and 1 plus 1 0, 1 gets carried forward here, and this 0 will be turned into 1. So once a 0 gets turned into 1, and when you take the bitwise OR, so this position will become 1, but in our answer we should have this value as 0 only. Okay, so for that, what we can do is a trivial solution is the last bit you can just change it to a 0, and the rest all keep it as it is. So 1 1 0 0, everything is same except the last bit. I'll just change it to a 0, so that when you do a +1 to this number, you will get something like this. 1 0 0 1 1. And to this, when you take the bitwise OR, you'll get the exact same number as this, because the only last number we have just reduced to 0, and plus 1 will add a 1, and when you take the bitwise OR, the 1 will get restored back. So this is a possible solution. So if your number, if you for a particular number, your answer can always be equal to num minus 1. So in this example also we can see, suppose for 5, your answer can be 4. And for 7 also, 6 can be an answer, but 3 is a minimum answer. So we will return 3. But one thing is for sure, that whatever number you have, the number minus 1 will always be a valid answer. We just have to find the minimum answer. So here we saw that we just changed the last. I think we need one more one here. Yeah, let me just change it. Yeah, 807 in binary, it will have another one. So like we discussed, the answer number will be same, except the last digit, we can change it to 0. So what if instead of making this bit 0, we can make the other one as 0? And let's see what happens in that case. So instead of making this 0, I'll make this bit as 0. So now to this number, if I add a 1, then let's see what happens. So 1 plus 1 0. So this 1 gets carried forward here, and the carry ends here, because 1 plus 1 is 1 plus 0 is 1, and the rest of the numbers will be the same. 1 0 0 1 0 0 1 1. So this is the number, and this is the number plus 1. So when you do bitwise OR, you will get the exact number, exact same number. So this is the case when you have changed this bit to 0 instead of this bit. So similarly, we can also change this one as well to 0, and you will get the same answer. So to prove that, we can say this bit as 0. And when you add a plus 1, the result will be, here you have a 0. 0 gets carried, 1 gets carried forward. Here you get 0. And whatever the carry is, it ends at this 0. So the carry ends, and after that, whatever the number is, the same thing gets copied here. And when you take a bitwise OR of these two numbers, 0 and 1, you get a 1. 0 and 1, you get a 1. And 1 plus 1 and 0, you also get a 1. So this is the numbers you can use. So I'll just write all of them. So first thing, you can just put the last number as 0. And next option is 1 0 0 0 1. So you can choose this number, this position to be 0. And finally, you can also choose this position to be 0. So I'll just mark it in a different color. So for the first option, you will have the last bit as 0. The last one will be turned to 0. For the second option, you will have the second last turned to 0. And for the last one, for third option, you will have this bit turned to 0. So these three are the valid answers, but since we want to find the minimum answer, we'll always pick this one. So that means this is the lowest bit, and the left one is the highest bit. So we'll try to make the biggest bit to 0 in order to minimize our value. So the approach is pretty simple. We'll just iterate the bits from left to right. And of course, the last bit will be 1. And we'll keep iterating until we have a 1. And as soon as you find a 0, the bit next to 0, which is this 1, you'll turn it to 0, and that will be your answer. So let's just see through our examples how this is happening. So in our first example, we have a 3, which is 1 1. So 3, you can just add a 0 here. This is also 3 in binary. So first you iterate here, it's a 1. Then you iterate on this, it's again a 1. then you come here, it's a 0. So once you find a 0, the bit which is next to the 0, you will turn it as, you'll unset the bit. So the answer will be 0, 0, 1, which is 1. Now similarly, if we check for 5, 5 in binary is 1, 0, 1. So first you'll start here, it's a 1. And when you iterate here, you found a first 0. So whenever you find a first 0, the bit to the right of it, you'll make it 0, and that will be your answer. So answer for this will be 1, 0, 0, which is 4. And finally for 7, this is 7 in binary. You'll again iterate. Here it's a 1, it's a 1, it's a 1. And here you see, you find a 0. So the bit which is next to 0, you will turn it to 0. So your answer will be 0, 0, 1, 1, which is 3 in binary. Let's quickly look at this approach for the other examples as well. So you have 11, which is 1, 0, 1, 1. So for this as well, this is a 1, this is a 1, and this is the first position from the right where you'll find a 0. So the bit which is immediately next to it, you'll turn it as 0. So this bit gets turned to 0, and the remaining bits remain same. So this in binary will be, I think, 9, and 9 is our answer. And then similarly for 13, this is 13 in binary. And this is the first 0 you encountered. So the bit next to it, you'll turn it to 0. So your answer will be 1, 1, 0, 0, which is 12 in binary. And finally, we have 31. So this is 31 in binary, and this is the first 0 from the right. And so that means you will turn this bit into 0. So the answer will be 0, 0, 1, 1, 1, 1. And this is 15 in binary. The answer is 15. And just note the special case. Whenever you have the number as 2, you'll just return -1. Now let's quickly code the approach. So first let me take the size of the array. And also create an answer. So for each number, we have to find the answer for the nums of I. So for that, let's just use a function, and in that we'll just pass nums.getI. And at the end, just return answer. So now we just need to fill the this function that will return you the answer for each number. So we have the function. We'll take number. So first thing, we'll handle the base case. If you have the number equal to 2, then you can directly return -1. So otherwise, you will iterate on the bits. So let me just write it again. 1, 1, 1. Okay, so you have to start iterating on the bits from right to left. So integer will have like 32 bits, so we can just run from int bit equal to 0, bit less than 32, bit plus plus. So this is bit number 0, bit 1, bit 2, 3, 4, 5, 6, 7, 8, 9. This number 807 has total 10 bits from 0 to 9. So we need to check all the bits from right to left. The first bit, that is 0. So for that, we can say if one left shift bit and number equal to 0. That so one left shift bit will give you, let's see how this is happening. So initially bit is 0. So one left shift 0 will be 1 only. Then one left shift 1 will be 1, 0. Let me write it on the left. So one left shift 2 will be 1, 0, 0. 1 left shift 3 will be 1 0 0 0, and so on. So when you run this loop, initially the bit is 0. So 1 left shift 0 will be 1. So this is the number, and this is the 1 left shift 0, which is 1. So both these numbers, you're taking a AND operation. So when you do the AND operation, since all the bits are 0, so all these values will be 0, and only the AND will be taken with this bit. So if this bit is 1, then your AND operation will result in some number. And suppose if this bit is 0, let's say I am doing 1 left shift 4, and I want 1 left shift 3. That means I want to check the third bit. So 1 left shift 3 will be 1 0 0 0, which is 1 0 0 0. And to this, when I do the AND operation, you'll get the result as all zeros, because this is the only one you have, and that also is being AND with 0, so you'll have a 0. So this is how we can figure out that whether a particular bit in a number is either either set or not set. So suppose if this number was not 0, if this number was 1, then when you do the AND operation, the result will be this. So the result will be non-zero number. So if you get a 0 number, that means the particular bit is not set. So by this condition, we see that this bit is a 0. So from our logic, we need to set the bit which is the right of it to 0. So to set the bit as 0, we can just use a XOR operation. So we can say number XOR equal to 1 left shift bit minus 1. So in this example, let's see what's happening. So we have bit equal to 3. So first 1 left shift bit will be 1 0 0 0. And when you take an AND operation, you get the result as 0. So that means you have found out that this bit is 0. So now you have to set this particular bit as a 0. So for that, what you'll do is you will do 1 left shift bit minus 1. So 1 left shift bit will give you this number, and 1 left shift bit minus 1 will give you this number 1 0 0. So this and this, you're taking a XOR operation. So let me quickly say what the XOR operation is. So XOR of two same numbers will be 0. So XOR of 0 0 is 0, 0 1 is 0. And then XOR of 1 0 will be 1, and XOR of 0 1 will also be 1. So here, since we want to set this bit as 0, so we are taking a XOR with 1 0 0. So we have all zeros here. So when you have all zeros, the number won't change. So all these numbers remain same. But here you see we are taking a XOR with 1 and 1. So for 1 and 1, you get the result as 0. So this is 0, and the remaining numbers will be same. 1 and 0 will give you a 1. 1 and 0 will give you 1. So the only number that is changing is this bit, which got turned into 0. And when you update the number, you can just break and return the number. Yeah, I think that's all. Let me just test it. The number. I quickly also want to do a dry run where for this number 7. So for the 7, when you are at bit number 4, which is 1 0 0 0, and you take the AND operation, you finally get a 0. So the bit is 4. So you take a XOR with 1 left shift bit minus 1. So 1 left shift bit minus 1 will be something like this, 1 0 0. So to this, when you take a XOR operation, 0, 0 will give you 0, 1, 1 will give you 0, 1, 0 is 1, and 1, 1 is also 1. So for 7, you got the answer as 3. So we can see for the 7, the answer is 3. Let me submit now. Yep, and it works. Finally, let's do the time and space complexity analysis. So first for time complexity, here we are just running a loop which will run on the array length. So this will be order of n. And then in this function, we are running a loop from 0 to 31. But this will only run until we find the last, like highest greatest bit, because after that it's a 0. So the loop breaks. So basically the complexity of this loop will be log of the number. So overall time complexity will be order of n into log of number. And coming to the space complexity. So for space complexity, apart from the answer array that we have to return, we are not creating any additional space. So space complexity, we can also say it is order of n. I also have the code in Python if anyone wants to view it. I'll add this in the description as well. And let's catch up in the next video.